Whoa, what a collision that was. Before I can talk to you about the collision itself, we need to go over two terms, momentum and the center of mass. Momentum is given by the Greek letter rho, which looks a lot like an English P. One common misconception about momentum is a lot of people think that as something travels, it's picking up momentum, so that when it hits something, it'll have a harder impact. But that's not actually the case. Take a bullet out of a gun, for example. When it is launched, its momentum is the highest it will be, and it is the lowest upon impact. This is because momentum is directly proportional to velocity, as it is the product of mass and the velocity vector. When the bullet is launched from the gun, it begins to slow down due to friction from the air, which makes the velocity slow, making the total momentum lessen. Knowing from 2D and 3D motion that the change in velocity over time, the derivative of velocity, is acceleration, we can see the change in momentum over time is equal to mass times acceleration. And we know from the forces video what mass times acceleration is equal to. That means that the sum of forces acting on an object is equal to the change in that object's momentum over time. We'll have a little bit more about that later. For now, let's discuss center of mass. The center of mass of an object is the point at which all its mass is evenly distributed around. With the bowling ball, it's nearly the geometric center. Now, I say nearly because inside of a bowling ball, there is a weight block. That is a large hunk of mass inside of the ball of a particular shape to make the ball flip as it goes down the lane. Mass is also taken out of the bowling ball for the thumb hole and finger holes being drilled in. This changes where the center of mass is actually located, but it will still be very close to the geometric center. The center of mass for a bowling pin will be somewhat close to the geometric center. The center of mass of an entire system, let's say our system, is this bowling ball and bowling pin. The center of mass of the system is essentially the center of mass of the centers of masses. Since the bowling ball weighs approximately 7 times more than the bowling pin, the center of mass will be about 7 times closer to the bowling pin, or the bowling ball, excuse me, than the bowling pin. The bowling pin is stationary as the ball is coming along to hit it. The ball is moving with velocity v0, so the center of mass of the entire system is going to be moving with a velocity proportional to v0, but not the same. As the ball gets closer, the center of mass also gets closer to the pin, but it also gets closer to the ball as the ball and pin come closer together. That's what's helpful about a special thing called the center of mass reference frame. That's when your frame of reference, rather than observing something happening from afar, and say with that video you just saw, you observed the ball coming in and hitting the pin. Seeing the pin was stationary and the ball was moving toward it. From a center of mass reference frame, you put yourself in the center of mass. So, with respect to the center of mass, the ball is moving toward it and the pin is also moving toward it. Since the center of mass stays proportionally the same to the ball and the pin are coming toward the center of mass at the same ratio. This makes complex collision problems easier to solve. A little more about center of mass. In order to find the center of mass of a system of particles, it is equal to 1 over the total mass, given by capital M top, multiplied by the sum of each mass times its respective center of mass location. So for a system of 2 particles, that would be m1x1 plus m2x2 all over the total mass. In our case, with the bowling ball and pin, it would be the mass of the ball times the location of the center of mass of the ball, plus the mass of the pin times the location of the center of mass of the pin over the total mass. Now going back to 2D and 3D motion, and those basic kinematics, and knowing what the derivative of position is the change in position over time, which is velocity, we can derive each term, mass 1 times the derivative of its position plus mass 2 times the derivative of its position over total mass will be equal to m1v1 plus m2v2 over total mass, and mass times velocity, as we just learned, is momentum. So the center of mass velocity will be given by 1 over the total mass multiplied by momentum of object 1 plus momentum of object 2. The two types of collisions we have are elastic and inelastic. An elastic collision, the objects bounce away from each other after the collision. They don't have to be going opposite ways, but oftentimes they are. In an inelastic collision, the objects stick together and they continue moving together with the same velocity after the collision. Now, if the sum of forces on the system that these objects are a part of is 0, then since the sum of forces equals a change in momentum over time, the change in momentum over time equals 0, which means that momentum is conserved, the initial momentum is equal to the final momentum. So now let's look at an example. You can see the full question on the website next to the link for this video.